We all know the story. Newton sits under the apple tree, the apple falls on his head, causing him to ponder why that happened, and bam! Newton invents gravity. To describe this crazy new concept, however, he needed a new language. And so came calculus. And after that, all the differentials and integrals and every other topic that makes calculus students cry. With all these tools, calculus is great at describing physics. Projectiles, volumes, kinematics, dynamics, and more. In our case, calculus is perfect for describing orbital mechanics. Let's look at the Milky Way. We're within a galaxy of 300 billion stars, 100 billion planets, and 7 billion people, all revolving around a big black hole. Despite all this chaos, however, everything follows the same few rules. We know that objects travel in elliptical orbits. This is Kepler's first law. While most people think of orbits as circles, they're actually much more stretched out. Take Halley's Comet, for example. At its closest point to the Sun, it's only a measly 85 million miles away. At its farthest point, however, it's 70 times that distance, 5 trillion miles. Kepler's second law says that objects cover the same amount of area of their orbital ellipse in the same amount of time, no matter what. This means that as their distance from the focus changes, so must their speed. When further out, the object will travel slower than when the object is closer to the focus. Now that we have those down, let's take a closer look at the black hole in the center of our Milky Way, Sagittarius A star. It's about 24,000 light years away from Earth. The stars closest to the hole have periods of about 100 years, while the furthest have some 100 million years for a complete orbit. Let's focus on one of the closest stars, called S0-2. For our project, we'll try to find the period of this particular star's orbit using differentials. Let's put the Milky Way in a graph. We know that our star was closest to the black hole in about mid-March 2002, at 117.7 astronomical units away. 1 AU is about 150 times 10 to the 9th meters, so it's still pretty far. We also know that its speed at this time was negative 1,670 AUs per year. Using this information, we'll find the period. We'll start out with a couple of basic formulas. We know Newton's famous second law, stating that if an object is accelerating, then a force must be acting upon it. More simply, a force equals mass times acceleration. Newton also invented a law of gravitation, comparing the force between two objects to be the smaller mass multiplied by the bigger mass divided by the distance between them squared multiplied by a constant g equal to 6.67 times 10 to the negative 11th meters cubed over seconds squared times kilograms. Now here comes the calculus. First, we need to balance our units. Our constant used these units, but the actual graph used these units. Using some simple balancing, we get a new conversion factor. Now we need to equate both of Newton's formulas, getting common m on both sides. We can cross this out. Using the position function of RT, that's the distance between our black hole and the star is our position function, and AT is our acceleration function, the double derivative of RT, and in vector notation, RT equals xti plus ytj, we can derive this twice to get the acceleration function. Using the computer algebra program Maple, and the initial position and velocity of our star at t equals 0 in March of 2002, the program shoots out specific table values after 1 year, 2 years, 3 years, and so on. To visually portray this, plug the position function given by Maple into the calculator, and an ellipse, exactly like the path of our star, comes out. Using these table values, it can be seen that it takes exactly 15.58 years for the star to return exactly to 117.7 AUs away from the black hole, giving us the period. So this poses the question: if we can use calculus to find orbits around black holes that we already know exist, what's stopping us from using calculus to find the orbits of objects and matter we don't know exist? Unlocking more secrets to our universe? That's for us to find.